Okay, let's talk about alkanes a little bit. And alkanes are saturated hydrocarbons. Hydrocarbons contain only carbon and hydrogen atoms. And the general formula for a chain alkane is CnH2n plus 2. And what this formula means is that N is the number of carbons in the molecule, and if you want to figure out the number of hydrogens, you multiply that number by 2 and then add 2. So let's say, for example, if you had a hydrocarbon alkane with 10 carbons, the number of hydrogens would be 2 times 10 plus 2. So pretty easy math to do in your head. So 2 times 10 is 20, plus 2 gives you 22. So as long as you know the number of carbons in an alkane, you can figure out the number of hydrogens very easily using this formula. And you'll be expected to know how to apply that formula. It's also important to note that the bonds in alkanes are carbon-hydrogen and carbon-carbon single bonds. So we only have single bonds in alkanes. There are no double bonds and no triple bonds. When we have a hydrocarbon with a double bond, we call that an alkene. And if we have a hydrocarbon that has a carbon-carbon triple bond, we call that an alkyne. But that's for another video. In order to relate the structures of organic compounds, chemists use a variety of formulas. And first of all, you should know what a molecular formula is. And a molecular formula simply lists the kind and number of each type of atom in a molecule, but it doesn't tell you anything about the bonding pattern. So it doesn't tell you anything about the actual structure or the way the atoms are put together. So say, for example, I have C2H6 or C3H8. These are simply molecular formulas, and they, again, don't tell you anything about the way the atoms are connected together. A structural formula shows each atom and bond in a molecule. So here we have two examples of structural formulas, and if you notice that this compound down here actually has the molecular formula C2H6, and this one down here has the molecular formula C3H8. But these structural formulas again show us every bond and how the atoms are arranged. Although structural formulas show the complete structure for a molecule, for large molecules, they can be very time-consuming to draw and take up a lot of space. And the way that we solve this problem is by using what we call the condensed formula. The condensed formula shows all the atoms in a molecule and places them in a sequential order that indicates which atoms are bonded to which. The following are condensed formulas for ethane and propane. So this first one here is ethane, and this one over here, this is propane. And what we did in the condensed formula is that we eliminate all of the carbon-hydrogen bonds. So we don't even show those, and we condense them or shorten them to these little CH3 and CH3s like this, and then we only show the bond between the two carbon atoms. Similarly, in propane, we have the CH3, CH2, and CH3. So again, we are eliminating all the carbon-hydrogen single bonds. The simplest representation of a molecule and the most powerful way to represent an organic molecule is using what's called the line formula, or some books call it the bond line formula. In the line formula, we assume that there is a carbon atom at any location where two or more lines intersect. We also assume that there is a CH3, or what we call a methyl group, at the end of any line, and that each carbon in the structure is bonded to the correct number of hydrogen atoms. Remember the rule, carbon always has 4 bonds. So if we take a look at this structure here, it might just look like a line, but remember, I said that at the end of every line, we assume that there is a CH3. Now I'm just writing this in here for instructional purposes, and we have the end of the line over here on the left. We also assume there is a CH3 there as well. So in order to represent ethane using a line formula, I simply would use a line like this. Similarly, with propane, we can assume that the end of a line here, we assume that this is a methyl or a CH3. We assume that this end of the line is a CH3. And any points where two lines intersect, we assume that there is a carbon atom there and that the carbon is bound to the correct number of hydrogen atoms. Now, if we look at this carbon down here that I've just drawn, this one right here, it has two bonds attached to it that are shown. But again, we assume that carbon always has 4 bonds. So how many more bonds would this carbon have to have in order for it to have 4 bonds? Well, the answer is 2, because 2 plus 2 is 4. And that is why at this intersection, or this vertex, if you will, down here, this is a CH2. So the way that we represent propane using a line formula is just by going like this, 1, 2, 3, like this. So you can see how the line formula is a very fast and powerful way to draw alkanes. As I mentioned in the introduction video, you must memorize the names of the first 10 continuous chain alkanes. So we went over the generic formula for alkanes, which is CnH2n plus 2. Now, and you have to have memorized when this N here, you have to have that memorized if it's any number between 1 and 10. So you have to have memorized when it's 1 carbon, we would have 1 times 2 plus 2, which would give us 4. So CH4 is methane. And then from there we have ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. And you must memorize all of these. Before we move on, let me show you a little trick here. So it says here for decane, you think, okay, 10 carbons, that's pretty intimidating. We have our molecular formula, C10H22, and here is the entire condensed formula shown like this. Another way to shorten that is you see that we have 8 CH2 units in here, 1, 2, 3, all the way up to 8. You can shorten that as is shown here. That's one way of doing it. But if I wanted to draw this using a bond line formula or a line formula, the way I would do that is that when my marker or my Apple Pencil, when it touches the screen, that's carbon number 1. So you see this dot, that's carbon number 1. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And that would be a line formula of decane. It's one of those things that you have to practice a little bit to get the hang of it. Here's some more examples of using bond line formulas or line formulas. It says, write the structural and condensed formulas for the following line formula. So here we have a line formula, and they even give you a name down here. It says here 2,2,4-trimethylpentane. We'll learn about how to give that molecule that name later on, but for now we'll just take the name as such. Now remember that at the end of each one of these lines, I have a CH3. So I can draw a CH3 on the end of each one of these lines. So I'll put a CH3, a CH3. In any place that lines intersect, I have a carbon. So there must be a carbon here, carbon here, carbon here. And remember the rule that carbon always has 4 bonds. Now if I look at this carbon right here, it already has 4 bonds. So I don't have to add any hydrogens to it. This carbon down here already has 1, 2 bonds, so it must be a CH2. And this carbon here has 1, 2, 3 bonds, so it must be a CH. So this is the way that they solve it in the book, is by drawing out the carbon skeleton, what we call the carbon skeleton, just by writing the carbon atoms and leaving the hydrogens out. And then they add in the correct number of hydrogen atoms. Either way works well. The main thing is that you get some practice in it in order for you to master the concept. The simplest organic compound that we can have is actually methane, CH4, which is one of those compounds that you have to have memorized, right? We go methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So you have to have methane memorized, so CH4. And you probably remember the tetrahedron from general chemistry. And since carbon has 4 bonds, it forms a tetrahedron. So these are different ways of representing methane and the geometry of methane. The first one is a Lewis dot structure. I'm not a big fan of this one here where they leave the dots in between like this. I prefer my students to draw the bonds in like this, right? Because every bond is the sharing of 2 electrons. And you should be familiar with the tetrahedron. Now, in B here, they're just showing the shape of the tetrahedron. And in C, they're showing the tetrahedron with dashes and wedges. Remember that when you have a line coming out like this, we call this a wedge. And when we have this kind of hashed line here, we call this a dash. You should also remember that the bond angles, all of the bond angles in the tetrahedron are 109.5 degrees. D is the stick drawing of the tetrahedral carbon atom. I don't like to use that a lot because the dash and the wedge are far superior, in my opinion, at representing the three-dimensional structure of the tetrahedron. And the last one is the ball and stick model of methane. And we're going to get some practice building models in the lab. These are just drawings of the molecules ethane and butane. So A and B are ethane, and then C and D are butane. And again, you're going to have these structures memorized. And the important idea here is that you understand that the dashes like this are going back into the page, and that the wedges like this are coming out from the page, and that all of the bond angles are 109.5 degrees because each of these carbons has a tetrahedral geometry. Here's the ball and stick model of ethane over here. And then for butane, you can see that butane, we have 4 carbon atoms, and you can see the dashes and the wedges, and each one of these bond angles, they're all 109.5 degrees. And then this is the ball and stick model of butane over here. Another concept you have to be familiar with is the concept of isomers. And many carbon compounds exist in the form of isomers. And isomers are simply compounds with the same molecular formula but having different structures. An example of isomers would be these 2 compounds down here, butane and methylpropane. They both have the same molecular formula. If you take a look at both of them, they both have 4 carbons and 10 hydrogens, but they have different structures. What does that mean? It means they are connected in different ways. You can see that all of the atoms in butane are connected in this linear fashion, whereas in methylpropane, I have 3 carbon atoms in a row like this, but then I have this branch coming down here with a CH3 group, or what we call a methyl group, coming off of it. So these 2 compounds are going to have different physical properties. That means they're going to have different melting points and boiling points, different densities. So isomers are compounds that have the same molecular formula but different structures. If we take a look at this table, it says here the melting and boiling points of 5 alkanes with the molecular formula C6H14. So all 5 of these compounds here are made from the same number of carbons, 6, and the same number of hydrogens. How they differ is the way the atoms are connected together. And look what happens when we connect the atoms together differently. They have different boiling points. You can see all the boiling points are different, and they also all have different melting points. What about the physical properties of hydrocarbons? The first thing, you have to be well aware of the fact that hydrocarbons are nonpolar molecules. And the reason why they're nonpolar molecules is because they have no polar bonds. The only bonds you're going to find in hydrocarbons are carbon-carbon bonds and carbon-hydrogen bonds. And neither of these bonds are polar, and therefore hydrocarbons must be nonpolar molecules. If you remember from general chemistry, water is a polar molecule, and you probably remember the rule, like dissolves like. And that is why hydrocarbons are not water soluble, but they will be soluble in nonpolar organic solvents. And if you're wondering what would be an example of a nonpolar organic solvent, a nonpolar organic solvent would be something like benzene or hexane. And as the course progresses, we'll get more familiar with different nonpolar organic solvents. Hydrocarbons also have low melting points and low boiling points. They're generally speaking less dense or lighter than water. If you've ever been to a gas pump and spilled a little bit of gasoline on a puddle, let's say at a gas station, you'll notice that the gasoline will float on the water. And so hydrocarbons, generally speaking, are less dense or lighter than water. Also, oil from an oil spill will usually float on top of the water. But you're going to notice that as the length or the molecular weight of a hydrocarbon increases, melting points and boiling points will increase, as will density. And there's good reasons for that we'll talk about in more detail later on. Carbons can be classified according to the number of other carbon atoms to which they are attached. So if we take a look at all of these carbons highlighted in pink here, so we have this one here, well, I'm covering them up with blue, aren't I? Anyhow, if we had all of these carbons that were pink, okay, you can see the first one is attached to one carbon and everything else is not a carbon. We call that a primary carbon. If it's attached to two carbons, we call that a secondary carbon. You can probably guess. If it's attached to three, we call it a tertiary carbon. And if the carbon is attached to four other carbons, and I'll draw that in here, then we have what's called a quaternary carbon. So that would be an easy question for me to ask you. I could point out to a carbon atom in a molecule and say, is this a primary, secondary, tertiary, or a quaternary carbon? Alkyl groups. An alkyl group is an alkane with one hydrogen atom removed. And when you remove that hydrogen atom, you name it by replacing the ane suffix with -il on the end. So if you remember methane, ethane, propane, butane, so on and so forth, if we remove one hydrogen atom from any one of those, we would get methyl, ethyl, propyl, butyl, pentyl, so on and so forth. So the methane molecule becomes a methyl group when we remove one hydrogen from it. And you might be wondering, well, what is this attached to? What is this CH3 attached to? Well, it could be attached to literally Avogadro's number of molecules, okay? So you need to be able to recognize that when we see a CH3, we call that a methyl group. And the more practice you get in nomenclature as we progress through the course, the more you will become accustomed to just recognizing and identifying methyl groups. Again, if we take an ethane molecule and we remove one hydrogen from it, we get an ethyl group. So here's our ethane molecule over here, C2H6. We have the entire Lewis structure shown here. And if I remove any one of those 6 hydrogens, I get an ethyl group. In the ethyl group, we can write it as CH3, CH2. That would be the condensed structure like this, okay? Or you can write it any one of these ways that are shown here. All 3 of these are perfectly fine. And if you're wondering, are these different because I've taken off different hydrogen atoms? The answer is no. These are all the same. Every single one of these represents CH3, CH2. And here we have it in a table form, the names and formulas of the first 5 continuous chain alkyl groups. We have the methyl group, the ethyl group, propyl, butyl, and pentyl groups. So far we've looked at the methyl group, the CH3, and we've looked at the ethyl group, the CH3, CH2. Once we get to a 3-carbon molecule, propane, and we remove a hydrogen, well, it gets a little bit more interesting because there's 2 different types of hydrogen atoms in the propane molecule. If I remove one of the hydrogens from the central carbon, I get this, which we call an isopropyl group. And if I remove one of the hydrogens from the end, I get what's called a propyl group. So you have to know the difference between an isopropyl group and a propyl group. When we get to 4 carbons, it can get even more interesting. So if I take butane, and if I remove one of the hydrogens from the end, I end up with a butyl group, like as is shown here. But if I remove one of the hydrogens from the carbons in the middle, I end up with what's called a sec-butyl group. And so you have to be able to recognize a butyl group and a sec-butyl group. And so far we've looked at the isopropyl group and the sec-butyl group, but we also have to be familiar with the isobutyl group. It's a good idea to make flashcards with these so that you can memorize the connectivity or the way the atoms are connected. And another one that you have to recognize is the tert-butyl group. The way that you can recognize the T-butyl or the tert-butyl group is that the carbon is tertiary because it's attached to 1, 2, 3 carbon atoms. An easy way to remember the isobutyl group is that the isopropyl group has 2 methyl groups on the end, and the isobutyl group has 2 methyl groups on the end. In fact, it even says it down here. If you look at this asterisk, it says the prefix iso or isomeric is used when there are 2 methyl groups at the end of an alkyl group. Another point of interest shown down here, it says the prefix sec or secondary indicates that there are 2 carbons bonded to the carbon that attaches the alkyl group to the parent molecule. So if you look at sec-butyl, you can see that this carbon highlighted in pink is attached to 2 carbon atoms like this. And finally, the T or tertiary means that there are 3 carbon atoms attached to the carbon that attaches the alkyl group to the parent molecule. Again, if you look at tert-butyl, you can see that this carbon is attached to 1, 2, 3 carbons.